We just saw that Ohm's law requires a concept called resistance, that every object, if you apply a certain delta V, you get a certain current, and the proportionality constant is the resistance. So let's see how we calculate this thing called the resistance. Calculate resistance. The electrical resistance specifically is the one we're calculating, and let's do it for a cylinder. Or you could say it's for a wire, because by a cylinder I mean something with a little cross-sectional area A and a length L. So there is our cylinder of some material. It doesn't actually have to be round on the end, right? Cylinder, technically this is a right circular cylinder, but you can make other shapes into a cylinder. You can have a square like that. And you might call that a beam. Let's see, there we go. But if it's got cross-sectional area A that's constant, and if it's got a length L, you're going to get the same resistance. It doesn't really matter. Okay, as long as you have a constant cross-section for some length, that's all we care about. We could even have a star here. Here we go. Here's a star. Oh. A. Wow, this is so worth your time. Here we go. There we go. A, cross-sectional area. Length. Oh, I made it too short. That's okay. Length L. They're all going to give you the same resistance. So the formula for resistance at long last, R, is a new thing yet again. Rho L over A. So I keep telling you I'm going to tell you something, and then I'm throwing something new every time. You'll never win. Rho L over A. Just memorize that. Rho L over A. R is rho L over A. Let's start defining what these things are. L, let's do the easy ones first. L was the length. You probably want to put that in meters. A was the cross-sectional area. You probably want to put that in meters squared. And let's see, rho. That's an important one. Rho is the resistivity. You can imagine that the resistance you get is going to depend on what the material is made of. If you made it out of metal, you'll have a really low resistance, likes to flow current. If you made it out of salt, you're going to have a high resistance. So every material is going to have its own property that affects its resistance. It's not just geometry, it's also the material, and that's where rho comes in. So rho is a resistivity, an inherent property of the material. Inherent property of the material. That makes up the resistor. Okay? And the unit of rho is ohm meters. So before I told you resistance, the one we're about to do is in ohms. That's basically V equals IR, so an ohm is equal to a volt per amp, right? But to turn this into a resistivity, into an inherent property, you have to multiply it by meters, basically because of this formula. If this is ohm meters and this is meters and meters squared, then you have 1 over meters here times ohm meters is ohms. So it works out, okay? So rho, then R, the final thing we're looking for is the resistance. The resistance in ohms. So ivities are properties of materials, and anses are properties of objects. If you've learned about inherent and intrinsic and extrinsic properties before, that's what we're looking at here, right? The density of a material is intrinsic. So it doesn't matter how much of it you have, what size you have. But if you have a certain sphere of a material, its mass is extrinsic. Right? It depends on the size. So here, resistivity is the intrinsic property. I wrote inherent, I meant to say intrinsic property. And that's true of any piece of that material. But if you make a certain geometry, a certain shape, then you get the resistance, which is the extrinsic property. And that's, of course, the extrinsic property is the actual thing. That's why that's the one that goes into Ohm's law. That's the thing you've actually stuck in the circuit. Okay? So often you'll be given the resistance of something, you don't have to calculate it, or sometimes you'll be given it's a material, and you get the geometry, and you look up rho, or you're given rho, and you have to calculate it. But this is the most common formula we use for cylinders.